On behalf of EOL, I'm pleased to introduce Dr. Gyuwon Lee. Dr. Lee received his bachelor's and master's in atmospheric sciences from Kyungpook National University in South Korea before earning his doctorate in atmospheric sciences from McGill University, where he investigated errors in brain measurements by radar. With research expertise in remote sensing, radar meteorology, cloud physics, and precipitation forecasting, Dr. Lee has worked as a weather officer for the Republic of Korea Air Force, radar scientist and operator at the J.S. Marshall Radar Observatory, and as an NCAR ASP fellow and scientist. Currently, Dr. Lee serves as professor and director for the Center for Atmospheric Remote Sensing at Kyungpook National University in South Korea, where he recently received a Service Merit Medal and Presidential Award from the Korean government and the Muksan Award from the Korean Meteorological Society. His research spans from warm rain events to winter orographic precipitation, investigating the uncertainties and improving upon precipitation type classification, retrieval and representation of drop size distributions, and numerical representation of the observed microphysics, combining field observations and modeling studies. On that note, please join me in welcoming Dr. Lee for his seminar, A General Double Moment Scaling Normalization for Drop Size Distributions, Remote Sensing Observations and Model Parameterizations. Dr. Lee, welcome.
Thank you for a nice introduction. It seems you got some information from ChatGPT, right? So it's great to see old friends, and so it's always like coming back home. So John actually came in, and then he was talking. Is it something what I did during my PhD? Yes. Some. So in the end, now it starts to get attention from the community, and people start to use it. So I did this one during the part of my PhD, and then we actually go forward for the remote sensing observation as well as model parameterization. So actually, we try to use so-called general double moment scaling normalization of drop size distribution for the retrieve of drop size distribution, and also we really switch existing DSD model within NWP model with this new parameterization normalization concept. So I would like to thank you to my coworker, Professor Kyosung Lim. She is the original developer of WDM6. So we now moving into the so-called KDM. So it's a new microphysical parameterization that will be used for the global as well as local scale weather prediction. And also my student, and also there's some collaboration with Mehala from CSU too. Okay, so I saw the Hugh is around here. So this is a slide. Oh, he's there. So he's from his review paper. So we are dealing with very complex processes in a very small scale. So when you have a strong updraft, we have condensational growth and collision coalescence, so-called warm lane processes. And also, if you have a cold temperature, it involves the ice growth processes in typical vapor deposition and riming and aggregation, and also fragmentation. Recently, there is some attention on the so-called secondary ice production. So that involved like so-called Harlem motion and fragmentation, collision, ice-ice collision processes, and all different processes got involved into the secondary ice production. So there is a trend, actually, people try to use some of secondary ice production information into the NWP model too. Today, I will not talk about that. So actually, we worked for many years to identify secondary ice production with the weather radar data set. And then, of course, melting is part of microphysics. So it will involve into the heat transfer, and also the ice growth and the warm lane process will cut into the heat transfer too. These are theory. So some of them are well known. Some of them are actually still in active, very active for the research. So if you look at in reality, it's more complex. So this is a weather system actually observed with the vertically pointing expanded radar. So, and the reflectivity field. So you see the convection here and stratiform identified the radar brightband. And then all those theory can get fit into these images. But one of the biggest issue is some of those processes are got, those processes are intertwined. Some cases like here, you may have more stronger collision coalescence breakup processes. And then if you go to the stratiform rain and the ice processes become more important, and then warm rain process become much less important. But if you have a lot of moisture in the near ground, then you have a secondary growth, so-called cloud collection. So outcome of these various microphysical processes is basically dropside distribution. So either in the sky or either at the surface too. So reality is just very complex. The question is how we can understand this microphysical process through the observation. So typically we can use in situ and remote sensing observation. Whenever we try to understand microphysical process with observation, we do the qualitative investigation. We call the fingerprint. So you try to see the image and, this is the signature of these processes. And then we go for the quantification. So we try to convert into the number and the mass information. And then we can use that into the, parameterize those information into any kind. But the problem is we have very limited observation. And also we have very small sampling volume, in particular for the in situ measurement from the aircraft. And then the problem, what we are dealing with here is that the processes are so complex. So, and also occurring in a very small scale in time and space too. And also there is unknown processes too. So this is how, to understand these processes and quantize and parameterize those information, we need to have a lot of information. And also we need the theory and observation. We try to link all of those information together. So let's see the complexity. So this is a typical rain event in 1st of June. So you see the bright band here, melting layer is about 2.5 kilometers. And then this period, we don't have any melting layer. So it's a pure warm rain processes. And there is strong convection here. And even in the stratiform, we are very common to separate the stratiform and convection. But the problem here, even for the stratiform event, you have a very strong bright band, which is indication of big drops. And also, some cases we have very light or very weak radar bright band, which is indication of very dense ice particle actually falling from the sky. So even for the stratiform case, there is so much different microphysics processes going on compared with typical just the terms stratiform. And then what we did is actually we had at the ground, we had the digitometer that measured the dropside distribution. And from there, we calculate the rainfall intensity and radar reflectivity. So and then we try to parameterize this information or this relations with one parameter. So basically, typical, the radar QPE. So you want to estimate rainfall intensity with the radar reflectivity. You know the known GR relations. This we call the single parameter description of dropside distribution. Then you see that we have a deterministic relationship. And in addition to that, we have a stochastic component. The question is, those stochastic component is either random or structured. If it is random, it doesn't really matter. You can do the spatial and temporal smoothing, and then all those information goes away. But the problem is not that simple. So now I add time information here. It's the same image, but with time with a different color. So starting from here to all the way down. So now you see the structure as a function of time. So with respect to this deterministic relationship, you have sometime early period, everything is below this line, and then goes up, and then coming down. So there is so much structure in time too. So basically the problem what we are dealing with is structured in time and space. So let's see what kind of structure, time scale, in this case, over this structure. So this is a structure function with the time lag, and also this is correlation with time lag. So you see the structure function keep increasing, and also correlation actually coming down. And then after 1 hour, we have 0.4 correlation. So basically, E-folding time or decorrelation time in this case is about an hour. Basically, in this case, all those variation or time scale structure, what you see here, we call it uncertainty in this case. So they are structured. It has a time scale of about an hour. This is a sort of climatology. So if you deal with this kind of uncertainty in climate sense, then you will have hourly structure. Basically, we are dealing with the DSD variability that has structure in time and space. And then basically this structure actually coming from the variability of drop size distribution. And furthermore, it's coming from the different microphysical processes. So let's look at we are dealing with the change of diameter. And also, we are dealing with the different width of spectrum and different number. Some cases you have a higher number concentration. Some cases you have a lower number concentration. And also, they have a completely different shape, too. So this is a complexity of a problem that we are dealing with. So this variability is actually coming from the microphysical processes. So depending on the different microphysical process or dominant microphysical processes, you will have a variation of all these drop size distribution. So what we need is we need to have better description of this variability. So what kind of function, what kind of the model actually we can use to describe all these variability. Okay, so we went for the two major field experiment. So these are one winter experiment and the other is a summer experiment. But there are multi-purpose for the field experiment, but today I will focus on those, the microphysical parameterization and retrieval or the understanding microphysical processes within this field experiment. So this is ICEPOP 2018. So this is a Winter Olympic Game experiment. So we complete, and we had a special issue. If you are interested, there's a lot of different precipitation types and density and orographic effect of snow, and all different information are there. So you can go for the special issue there too. And now we are running the summer experiment. We call the Korea Precipitation Observation Program, K-POP. So it's a pretty good name. So we want to keep doing K-POP MS, K-POP ES. So right now we are doing the K-POP ES. It's a lake effect snow experiment at this moment. But this one, K-POP MS, is a mesoscale convective system experiment in Seoul metropolitan area. So we had international field experiment in 2023, and we want to repeat 2026. So these are scientific challenges. We want to handle it. First, we want to develop so-called observation-based analysis field. So if you do the so-called reanalysis, they have very strong constraint with the model. So that the mask some understanding of real processes. So we want to really focus on observation itself and want to have a high resolution analysis field to understand the dynamical and microphysical processes. And there is high resolution DA, and also some linkage between observation, analysis, modeling, and verification. And another ultimate goal is we want to advance microphysical processes and also their parameterization development too. So today I will talk about two topics: microphysical processes and how we actually advance microphysical parameterization in NWP model with the abundant observation for the two experiments. So these are, I will go for the very simple. So these are observation network for the K-POP MS. So this is sounding observation. So we have white one is operational sounding. So they do the 4 times per day. And we had special observation from KMA, which is Red Cross. And then another blue one is a special observation focus on the boundary way only. So it's we call the storm tracker that developed from the Taiwan. So we launched many sounding every 2 hours or every 3 hours to understand the thermodynamic structure within in the below the 3 kilometer. And then we have the remote sensing observation coming from the window profiler, Doppler radar, cloud radar, and the weather radar system too. So in that way, we can collect the entire data set from the clear air condition all the way to the precipitation too. And then we have over 23 sites of microphysical instrumentation. So this one has the possible and 2 DVD, and some location has MRR. So in that way, we know the particular structure and the ground information of microphysics too. And also, people was interested in the lightning occurring in the moisture-rich environment. So we have LMA network around this area too. And then this is supersite setup. So this is our focus is around this area. So around here we have Incheon International Airport. So around the Incheon International Airport, we set up the supersite, about 5 supersites. So these are equipped with Doppler lidar, window profiler, and cloud radar, and also the weather radar system too. And also a lot of different ground observation of microphysics too. So and then now let's move on to the microphysics. So how we can describe the variation of those complexity? So we can actually predict evolution of drop size distribution. We call it ND and of D here. So coming from the Gross equation, so there is a advection term and auto conversion, cloud collection breakup, all those processes that I described in the first slide. So the number concentration over diameter actually change as a function of all these microphysical processes. And then, so if you predict ND as a function of time, we call the beam microphysics in NWP model. So actually, all the drop size distribution described with the number concentration as a function of diameter, and then you see how these DSD actually change with time. And then the problem here is, so the advantage of this one, you don't need to have any predefined functional form of drop size distribution. But the problem is we have to deal with the bins of x-axis. So it's computationally extremely expensive. And then the people actually now used to the so-called bulk scheme. So bulk scheme based on the so-called moment. So the nth moment of drop size distribution. So it's an integration of drop size distribution with d to m power. So nth moment. And then you try to predict or describe the nth moment of drop size distribution, how the nth moment of drop size distribution actually change with the different moment order. So right now, in the most of NWP model, they use 0th moment and third moment. They try to use M3 and 0. So that's how actually predict the precipitation or drop size distribution. And then in this equation, actually, we try to predict nth moment as a function of time. And the good thing about it is we have to, constrain the predicted moments in this case. So you can have like a 1 moment prediction or a double moment scheme. So it depends so how expensive you can tolerate. But the problem in this scheme is it requires specific functional form of drop size distribution. So typically, gamma functions is used. So the problem coming from this one in the current microphysical parameterization schemes. So I will show how we can actually improve by switching this gamma function with the double moment scaling normalization. So this is an example for the WDM6 that developed from Korea, my colleague. So in the ND, they use a gamma function, so shown in here. So gamma function has 3 parameters, N0, N0, mu, and lambda. So, but imagine you use double moment, okay, 2 single moment or 2 moments. Then DSD model is 3 parameters. So basically, you need to have some assumption on there. So if you have 2 parameters, then one of these parameters should be assumed as constant. Typically, mu is fixed. That's what happened. So, but the problem is if you fix mu, then you always consuming like a mu equal 1 or 3, then all DSD will be like this. You will not have any kind of this kind of DSD. And then in microphysics, we need to have a lot of assumption on the microphysical parameter. So like VD, pole velocity and diameter, mass diameter, relationship and density of species, how many species you are using, and also efficiency of those processes that I described already. And so we try to actually solve all these issues, basically, from the observation. So how we can constrain these all information with the observation. So that's what we are trying to do. And then first approach is we want to replace this one with double moment scaling normalization. So what is double moment scaling normalization then? So there is some mass here now. So we're talking about drop size ND. So this ND can be represented with any way, like M0 multiplied by the probability density function, okay? So M0 is a zeroth moment. So you have a total number of drops multiplied with the PDF. Then PDF can be any functional forms. So you can use either gamma function or generalized gamma, whatever function you can use it. So, but here we don't assume any functional form at this moment. So what we try to do is we just assume the multiple power law. So there is, let's say, you know already, the old later hydrology, they know the GR relationship. GR relationship is defined as a power law, okay? And also in a lot of meteorological parameter, they actually assume the power law too. So here we assume the multiple power law between nth moment and I and j's moment of drop size distribution. So if you assume this one, then you can immediately derive so-called generalized double moment scaling normalization equation. So I will not go to the detail on how we can derive it, but in this equation, this is a simple way representing double moment scaling. So here, ND is same as here. So the first term here is we call the characteristic number concentration, which is the same dimension as this one. And then diameter is normalized with the so-called characteristic diameter. So, but these characteristic diameter and number concentration can be defined with any combination of 2 moments. So if you are interested in LiDAR, then you can use the low moment, like first and second moment, or first or third moment. If you are using weather radar, you can use the 3 and 6 moment. So it all depending on what types of moments you can actually get from the remote sensing. And then from this equation, you can normalize ND with N0 prime, okay? So N0 prime actually go to the left-hand side, and then now you have normalized drop size distribution with N0 prime. And diameter also normalized with the DM prime. So when you do the normalization with the characteristic parameter, then in the end, you will have H function. The question is, H function is whether it's unique or it's a vary in time and space. So from this formulation, so actually, the equation actually comes very nicely. So since you know the H function, then you can get the moment of nth function, okay? H function. So nth moment of H, okay? It will be the C value. C is actually coefficient of a multiple power law. So in this equation, coefficient is coming from the normalized DSD shape. And exponent of a multiple power law here, they are solely determined by moment order. Okay? So these are constant. So, and then this one coming from the hx. Let's say hx is a unique function. Then all this one and this one, they are all constant. Okay? Then all the variation of nth moment coming from the I and j's, variation of I and j's moment. Okay? or variation over N0 prime and Dm prime. So we try to use generalized gamma as a PDF, and then we come up with the H function, looks like this, okay? Okay, let's try to apply this one into the actual data set. So these are about 5-year DSD measured the ND from the South Korea. So you see the variation here. So almost a 3 order, how many order? It's a 3 order or 4 order magnitude variation. And also here you see some artifact there. So it's coming from the limitation of sampling volume. So actually you have all the way down the 0 drops all the way down there too. So in the actual observed DSD, you see so much variation. So that's coming from the shape change, number concentration changes, and diameter changes. If you apply double moment scaling normalization, so y-axis is normalized with N0 prime, and diameter is normalized with the Dm prime, okay? Then all these variations come into the very compact way. So now you can define very well-defined so-called H function. So the variation around Hx is very little compared with the original drop-size distribution. So we reduce the variation in the y-axis, even in the x-axis too. And then the next question is whether Hx is universal, or they are stable enough, we can assume Hx as a constant. So this is coming from the actual data analysis. So red one is from Korea for long period. So here is data set here. And the blue one is from the Oklahoma. So these are two extreme different climates. So we have a very moisture-rich environment and a pretty dry environment. So from there, still Hx function, they're more or less same. Basically, mean Hx function does not change. So basically, what we can do is we can assume Hx function as a constant. Okay? Or we can use any unique H function. Then if you assume the H function as a constant, then only variation remain as two moments, Mi and Mj. We call it the reference moment. So we have a stable Hx, and with this formalism, what we can do is we can explain most of significant variation of drop-size distribution. Okay, and then there is another issue, parameterizing in this way. First one is observational limitation. So this is a climatological drop-size distribution measured with the 2D two-dimensional video digitometer, which is commonly used for the research. And then this is again for the long-term observation from the perceiver, okay? So they have two different principles, but the problem here is, look at here. So there is a fallout of number concentration at the small diameter. So this is coming from the instrumental limitation. So it doesn't have enough the sensitivity to detect small particle, and also there is effect of wind drift. So there are all different issues there too. So due to that, the major DSD has a lot of issue. So there is it limit the modeling the Hx function with such kind of major drop-size distribution. And then what we are trying to do is actually we try to solve those issues with the small particles. So we call the drizzle particle. So we try to combine two data sets with the 2DBD, which is the best practice at this moment, and also the MPS that measure micron size particle. So they are co-located and we measured for long period. And then those are two instruments. Of course, they provide completely different information. So what happened here, so the red one, the solid line, the dashed line here is 2DBD measurement. You have a lot of lack of small particle here, so which is not represented well with the observed DSD. But now what we did is we combined two information, MPS with the 2DBD data based on the statistical uncertainty of each instrument, and then we come up with the solid line. So now you see this shape, like this color is different reflectivity, so you have a nice shape here. So you have two peaks in small size. You have another peak in the medium size. So it's so-called, there is a very nice, well-defined S-shaped drop size distribution. So now we have a sort of filling gap in what we stored in the drizzle size. So this will be the DSD we actually parameterize. And then this is a different way of showing. So this is average drop size distribution for the entire period, 2dBd, red, and this is combined DSD. Even you see the peak here. So this is I'm not go detail, but this is we call the breakup peak. Due to the collision coalescence, and then you have a breakup. So due to the breakup, you have a particular mode that has that generating particular size of drops. So now we have a combined data set. So this is HX from the 2dBd, and then this is HX from the combined drop size distribution. So this is coming from 2dBd, MPS. So we want to model with this data set. So this is how it looks like. HX, so 2dBd is red. So typical gamma shapes, which is not true. So you see this shape now. So the green line will be modeled into our development. Okay, so. And then if you do the double moment scaling, then you can reduce uncertainty up to below the 30%. So even you can go further for the triple moment scheme, so then you can reduce the error below the 20%. So that's what we can tolerate. So if you have the computational resource to do the triple moment, then I recommend go for the triple moment scheme. But if you still rely on double moment, then I recommend go for the either 2 or 6 moment. In terms of radar data simulation, I recommend go for the 3 mixing ratio and radar reflectivity. Then that will give you the direct data simulation way. Okay, let's go back to the microphysical parameterization in NWP model. So I'm talking about WDM6. From there, so we actually go to the so-called KDM. So we call the Kyungpook National University double moment 6 class. So we do a lot of modification now. So the WDM6 wasn't originally full double moment. So it has a different moment prediction for the ice and the rain. So we go for the full double moment. We try to optimize all these, the microphysical parameter from the observation. And also we introduced the predicted graphel density too. But today I will only focus on this one. So what happened if we replace existing drop size distribution, gamma distribution with generalized double moment normalization? So we will use M0 and M3 to still, we don't change any predicted moment, but still only we use moments or the DSD models. So here we don't have any assumption on the mu or N0 and lambda, so we don't need to fix mu. So instead we only fix HX, so which is less variable, very stable in a different climate too. So here in the literature you will see the GDMN. So this is it's a different version of a KDM. So we complete all these, or we are combining all these, then GDMN will be, in the end, you go to the KDM. So this is a simulation for the event, 6th of August. So with the observation, radar observation in original WDM6, and this is with the KDM. So here, so if you look at the radar data here, so you see the strong precipitation here. Actually, they propagate into the southeast. So that's the key here in the actual observation. But if you look at WDM6, this strong cell does not propagate into the southeast. Even they have more trend to moving into the east. But if you look at the KDM, they're actually moving into the southeast. And also, if you look at the location, it's further south. So what happened here, actually the precipitation produced the cold pool actually pushed so hard, so it put into the proper location in the KDM prediction. So this is a 6 to 8 hour forecast. And then, but we are not really focused on the predicting the precipitation better way with this new microphysics schemes. We want to focus on whether we can properly produce microphysical processes. So one of the key is growth. So I'm talking about all those ice and warm name processes. So if you look at the vertical structure of radar reflectivity or precipitation, that has information on the growth processes. So here, left-hand side is a radar, so-called CFAD, from the one scanning radar. So you see the reflectivity grow in general way, and then you see the decrease of radar reflectivity due to the evaporation here. So this slope here actually represent ice processes. You have a strong depositional growth. If you go to the around here, minus 15 degrees Celsius, and then you dendritic growth, and then rhyming and aggregation kicking up, that change the slope of radar reflectivity. So that's a reality, actual observation. So this is a simulation from WSM6 and WDM6. The problem here, you see the slope here. So the slope is completely different. So basically what it says is it, as an outcome of all those complex microphysical processes, those growth processes not produced properly. Okay? That's what we want to really see through this simulation. And now I will show the actual, what happened with the new scheme. So this is the event I showed earlier. So this is the radar CFAD again from this location here. So we had the full, the 240 kilometer scan. So here you have growth around here, and then growth rate become slow down around here. And this is WDM6, and this is KDM. So look at the growth rate, okay, in snow. So originally it was too steep, but now you have the slope become much more or less similar, okay? At least we start to produce proper growth rate in the ice. And then the other issue is we have too much precipitation at the ground. So the reflectivity is between 40 to 50 dBg, but now that all those high reflectivity actually goes down between the 30 to 40 dBg. And then the other issue is the warm name processes, okay? So here, so in the reality, you see the decrease of radar reflectivity, which is representing evaporative cooling, okay? Evaporation. So that's not produced here. But with this new scheme, you see the decrease of radar reflectivity with the decreasing height. So now we are pretty confident in terms of microphysics or the growth processes, we have proper the simulation in NWP model. But still we have problem. So starting point here, so it's too high compared with observation. So it's something to do with the generation of ice particles. So we need to handle on that problem later too. And then let's see what's the impact in the microphysics in these two different types of simulation. This is a mean diameter, volume weighted mean diameter from the WDM, and this is KDM. So look at the scale here. So mean diameter way too high here. So it's a range. It's a 20 centimeter or 2 centimeter or 3 centimeter, not realistic, okay? So now KDM, we reduced the mean size, but still it's about 8 millimeter to 10 millimeter. It's a little bit big. So mean size should be much less than the 3 to 5 millimeter. So we still need to work a little bit on that. And then in terms of a mixing ratio change, so this is a mixing ratio difference between the KDM and WDM. So you see so much increase of a rain mixing ratio all the way from the 0 to 9 kilometer. So this is just simply changing the DSD model. We didn't change any efficiency, anything, just the DSD model, and then we rewrite the entire the interaction, the processes. And then this has a huge impact in the heat, okay? So this is the temperature difference between two models, two parameterization. You have heating here, and you have cooling. So this is evaporative cooling. Imagine, so now with the new scheme, we produce a precipitation band in a proper location. That's coming from the proper evaporative cooling. So they actually push into the right location. And then we have a significant heating in the middle atmosphere. So that's coming from the increase of rain mixing ratio and number concentration of rain. Okay, that was from some result what we are doing for the NWP parameterization. So now we move to the radar remote sensing. So we come up with the machine learning estimation of drop size distribution using the double moment scaling DSD. So we used about 10-year data set, build up the T matrix. We introduced a random noise to make a realistic observation. And we tried to predict this or the estimate N0 prime and DM prime in the double moment scaling with all this information. So these are radar measurable in the pixel, and then those are not sufficient. So what we did, we want to have a spatial information. So we did a spatial average or temporal average to get the proper information in space and time. And this is an example for the retriever of N0 prime and DM prime, N0 prime and DM prime here. And then if you have a drop size distribution from N0 prime and DM prime, then you can get the rainfall intensity. So red one is our techniques, and the black one is original techniques commonly used. And then the black one, gray one is original techniques, and then black one is actual observation at the ground. So you see the red one is pretty well matched with observation too. So we are pretty confident our retrieval technique based on machine learning is better, to represent all those drop size distribution. And then we try to understand the microphysical processes by following the storm cell. So let's say you have a warm convection develops, and they move to the different location and try to see how the microphysics evolve as they actually go into the different stages. So we do the Lagrangian cell tracking. So we had two radar, so of expand rate, and then what we did, one radar actually do the general monitoring, and then the other radar actually is from the monitored reflectivity field, we identify the cell of interest, and then we try to do the RHI only for those focused convective cells. In that way, we can follow those cells all the way from the initial development all the way to the dissipation. Okay, this is a time snapshot of reflectivity and retrieve the DM prime and N0 prime. So reflectivity, we are actually focused on this small cell here in the red shown. So reflectivity increase all the way up and then decrease again. So we will focus on this cell. If you look at the DM prime and N0 prime, DM prime actually increase all the way up and then decrease again. And if you look at the N0 prime, they slightly increase, but you don't see much increase over N0 prime, and then slightly decrease in the later period. So this is animation for the individual cell. So what we did is, since we tracked the individual cell, so individual cell, we know where is the maximum radar reflectivity. We did RHI. So this is the RHI scan for the maximum, through the maximum reflectivity cell, maximum reflectivity pixels. So radar reflectivity and differential reflectivity and retrieve the DM prime and N0 prime. I will stop somewhere around. Can I stop here? Yeah, here. So you see here, well, for example, in this cell, okay? So you have high reflectivity, high GDR, but little reflectivity GDR here. So that gives you the high mean size. Particle size, mean size is huge, but below here, particle size is dramatically reduced. And then if you look at N0 prime, so you have increase of N0 prime. Number concentration is higher. Here, number concentration is much lower. So you have a high large DM prime and low N0 prime. So you see the systematic change there, even for below this area where the convective cell is below here. So you see the opposite, so the low DM prime and high N0 prime. And let's look at the strong reflectivity core. Yeah, I will try it again. So here, so you have a high reflectivity on GDR, so that provide a high DM prime, mean size. And then if you look at here, this H, you have very low the N0 prime. So number concentration is very small, so you have like a very broad distribution like this. So this is a snapshot of actual retrieved drop size distribution. So this is, again, we try to see how they looks like. So we will focus on this small cell here. So this convective cells just start to develop, and they go mature stage and slowly go down again. So you see this is a storm relative Doppler velocity. You see the very strong convergence around here. So convergence becomes stronger in the mature stage here, and then become weaker later on. So in terms of DM size, mean size, so in general, mean size increase for this cell, and then decrease. And then N0 prime, so N0 prime pretty low in the developing stage, and later you see the increase of N0 prime, and then again decrease. So you see the systematic change of DM prime, N0 prime as a function of stage of life cycle of convective cells. So since we tracked individual cell, and then we followed those cells all the way from the developing to the all the way to the dissipating. So we come up with for the so-called the cell average reflectivity and GDR and DM prime and N0 prime from retrieved information. So this column actually coming from the many information, many retriever for the individual cell. So here, so in general, reflectivity increase, so go to the developing stage, mature stage, and GDR has a maximum around here too. So DM prime has a maximum in the mature stage, and then N0 prime had a minimum in the mature stage. But interesting is if you look at the N0 prime, so you can clearly see the cloud base, even for this radar measurement. So here, this is cloud base. You see the dramatic change of N0 prime and DM prime in the cloud base. So above here, so you see the general increase of DM prime and decrease of N0 prime. They are more or less very smooth within cloud. But what happened in below, so when they just, particle actually just leave the cloud base, and then it's now it's not within cloud, it's outside cloud, and then immediately you see some abrupt change of N0 prime. N0 prime dramatically reduced, and then the DM prime dramatically increased. So basically, within cloud, outside cloud, you have a different interaction, the collision coalescence process actually going on, even for these warm name processes. And then another interesting feature is here. So in the developing stage, around the cloud base, above here, if you go up, then DM increase, but you don't see much change in N0 prime. But if you come down, there is the opposite. So basically, the DM prime increase, N0 prime slightly decrease. So with respect to this cloud base, DM prime, for the developing stage, you have a different mode of growth, basically. So let's look at a little bit more detail on this. So since we have DSD, retrieved DSD, then so we can see how those DSD actually evolve from the all the way top to the ground. So that's how you looks like here. So this is the top of cloud, and this is near surface. So see the evolution with the height. So this is for the developing stage. So let's look at the warm color here in the near surface. Near surface, you have a reddish color here. So basically what happened is, so when in the upper part here, it's steep, and then it becomes broad. So the number concentration in the reddish color actually decrease here and increase here. So you see the collision coalescence process there. But if you look at the blue color, bluish color, then this is a blue color here. So you don't see much change in number concentration here, but you see the increase of size. So basically, it's a condensational growth. So you see the even developing state, you see the two mode of growth in the warm lane. And then this is a mature stage. So look at how broad drop size distribution. So you see in the upper layer, you have very narrow distribution, steep distribution. In the lower layer and around surface, you have a very broad distribution. So number concentration goes down, and number concentration in the big diameter actually goes up. It's a typical collision coalescence processes. So we have a strongest collision coalescence process during the mature stage. And then if you go to the dissipating stage, then this broadening becomes much weaker, so collision coalescence become weaker. So this is what we see from by just looking the convective cell, following the cell, and then how those microphysical processes actually evolve as a function of different stages. And this is a different way of looking into the microphysics. So we try to see the N0 prime and Dm prime, how they change with height. Okay, in the early period, you see so much variation in x-axis. Basically, size changes, but number concentration doesn't change much. Basically, it's a condensational growth. But if you go to the mature stage, now you have both. Number concentration actually changes so much, and also diameter changes so much too. So you have both collision, coalescence processes, and breakup. And then the later period, so the variation in diameter is much less than the y-axis, but number concentration change. So collision coalescence become weaker in this period. I think so. We went through we had the main two-field experiment. We tried to use those information to parameterize a DSD model and try to link them into the NWP model. And this will give us the understanding microphysical processes and also better way of advancing the parameterization schemes. So we will fully further collect all the data set, and then we go for this direction too. Okay, thank you.
Thanks, Gyuwon, for that very comprehensive seminar. A quick reminder to those online, we'll take your questions in Slido, and I'll read them out. Do we have any in-room questions?
Yeah, thanks for the amazing talking. So I have really interesting about like a Cadian scheme. So I have a question. In a Cadian scheme, we are like fix the h of x, right? With the 2DVD and the MPS data set. So it's like so because your research show like they can like enhance the evaporation. Is this because like for the h of x, if you are including the MPS data, so you have like a lots of like a drizzle part in your distribution, so that's why you have like more small droplet.
Yeah.
And
first one is, if you regardless of your observation, let's say observation measure drizzle size very well, but still you use a wrong DSD model, then you cannot get such kind of effect. So you have to have a right observation, and you have to model those right observation with the right models.
Yeah, I understand. So my follow-up question is like, because I think so, if you like still fix even like you do the normalize, but if you fix your shape, they will get like some process you will like be wrong. Because your cloud will have like different period or different higher level will not have like the evaporation. So do you think like if they can like use like anywhere to like avoid like the fix of the shape in your microphysics?
Right now, with the double moment, there is no way.
Okay.
Because with the two moments, only you can do is either you change in this direction or this direction. So you need to just change slopes. So if you have another one, then you can constrain the different ways. You can have a different slope in this large size and small size.
Yeah.
So I think that's the only way you can do it.
To the more triple moment or even like more?
Yeah, triple moment or multiple moment.
Hi, Gyuwon. Nessa. Great talk. So one clarification question. You applied the double moment normalization in the model to both ice and liquid, I think, because you were showing the big changes aloft that were clearly associated with
right
ice.
now, it's only rain. So we are implementing the graphel and snow too.
Okay, in that case, why do you think you were seeing
So-
that change in the slope?
Because you have a rain all the way up,
Okay.
So rain mixing ratio starting from around 9 kilometers.
That was directly from
That's
rain,
the
not
effect of
from
that.
interactive with ice.
Right,
Okay.
yeah.
The other question I have is kind of a follow-up to the question about going to multiple moments. What do you think the value would be of going from 2-moment to 3-moment normalizations? Because the 2-moment normalization accounts for probably rough 70% or so of the variance.
Yeah.
But with 3-moment, you can probably push that to 90, 95%. Do you think that there is value in doing that
Yes.
for the cost?
Yeah.
Is there a plan to implement the 3-moment normalization into the
I
scheme?
keep talking with Professor Lim more than a year or two, so she's not still persuaded. So, but the question is, we want to modify HX function with the third moment. That's my idea. So.
Okay, so that's sort of in the works, I guess. Yeah. Okay, thanks.
Great questions. Next.
Wow, it's a lot of math. Okay, so you're only doing rain, and so obviously in some of your observations in the different your initial picture with all those different processes and things reaching the ground, how did you avoid getting water covered, ice particles mixed in, and so there were so many variables that yet you were able to take that and then boil it down. So let's just go with the way that you actually got that parameterized that stuff. It was only with rain, and those are measured from some kind of drop the 2D video distrometer or something like that.
So the most of parameterization actually has different species of particles. Like they have snow and cloud and rain, graphel, and hail. So right now, the most of those modeling done separately. So that's why we are doing that one. So original scheme that we are based on is also has 6 species too. So there is an issue, of course. So in the nature, that doesn't really work well. Some case you have like a water-coated, the ice particle, some cases, like hail. So they cannot be produced in this way. So usually they actually freeze in this NWP model. But there is a way actually the Hugh and Jason working on, they have a P3. So without introducing species, everything can be explained with density. So you have a mixture of water and rain, water or rain. Then you have high density. So you have tag onto the density information for the individual particles. So that's a different way I can handle it.
And if you just did snow by itself or some kind of ice particles, then the big variable there is the density of it. And so especially when
Density
you're
and velocity.
And so
Yeah.
you think you can sort all that stuff out also.
Yeah. So these are all the uncertainty we are actually putting into the model.
So is the power of this collapsing the drop size distribution, is that into understanding microphysics? Or let's say if I'm running SPOL and I want to make a better rain rate estimator, can that be used to then, what would it do? It would tune the coefficients on Z, ZDR, KDP.
Yeah.
Is that an application you're working on, or?
Yeah. So this work actually based on double moment scaling. So I will have a seminar on Thursday on that. So either single moment or double
gotta do
moment for
another seminar?
microphysics or remote sensing retrieval. Okay, so in a word, if you want to retrieve from those information with the dual pole or remote sensing observation, then go for the double moment scheme. But if you want to understand the microphysics, we call the generalized single moment normalization. So that's a better way, actually, getting more information on microphysics. So that's the conclusion.
I better stop here before I get into trouble.
Thanks for the great discussion, everyone. So that wraps up our hour. Dr. Lee is in town for another week or two, so please do continue conversations offline. Let's thank him one more time.
Thank you.